run off and leave anybody, but I don't want to waste your time either. So if I'm going too fast, raise your hand and say, can you slow down a bit, or say that again, explain that again. So if you need me to explain something again, it's up to you to tell me. Otherwise, I'm just going to keep going. All right. So what's a set? A set is just a collection of objects. In our case, it's normally numbers because we're in a math class. Right? So a set is a collection of objects. In our case, we're talking about sets of numbers. An element is a piece inside a set. In parentheses here, we're going to put the notation for element of, and it's the lowercase epsilon. So it's like, to make that Greek letter, make a lowercase c, and then just put a little line in the middle of it. That's a lowercase epsilon. That's notation for element of, okay? And we're going to use that notation some as we do some work here. All right? Sets are normally written in set braces. Set braces are not square brackets, not like that. Set braces are the little, some of you may, I like to call them curly braces. I don't know why, but that's what I've always called them. But they're set braces, and you'll hear me call them curly brace. So it's a little curly brace. So you got one on the left, one on the right. Some people end up making them like that, and it looks like threes backwards. That's not curly braces. Try to write curly braces the right way. I'll try to do a decent job of drawing them. Sometimes when I get in a hurry, they get a little squiggly, but I'll try to do a better job of that. So set braces. So if you see those braces, you know everything on the inside is a set. That's in mathematics. That's what that means. Okay. So an example, first example of the semester. Here's a set. We'll call that set. We'll give it a name, S, and do curly braces. 1, 2, 5, and 7. Just some random numbers put inside of a set. That's all it is. No rhyme or reason to that. Just some numbers. And with that set, we have a name for that set. So when we talk about an element of that set, let's say 2 is an element of S. That's how the way you read that is 2 is an element of S. That's the words that go with that mathematical statement. 2 is an element of S. That means 2 is inside of that. 3 is 3 in S. Is it an element of S? No. So if we want to say something's not an element of a set, do the little epsilon, and then in math, to make something not, you put a slash through it. And I used a different color slash, but it doesn't, you don't have to. And the colors on this particular projector are pretty chunky for some reason. It doesn't pick up the colors very well. And the cable is the problem. All right, so 3 is not an element of S. That means it's not in there, okay? So just a slash through the epsilon is what that says. All right, now, when we talk about sets, there are different kinds of sets. There are things called a finite set, F-I-N-I-T-E, and then there's an infinite set. Okay? Two different things, okay? A finite set, does anybody know what the word finite means? That's right. There's only a certain number of them, okay? So there's a limited number of elements. That's the way we want to define that. think about it as you can count how many there are. They're like our set that we had an example of here. That would be a finite set. It has 4 elements in it. That's finite, right? An infinite set, well, what's the prefix in? What does it do? Any English majors in here? The in is the opposite. The opposite of finite would be infinite. So opposite of limited would be unlimited. All right. So an unlimited or unending, maybe it's a better way of saying that since it's numbers that we're dealing with, number of elements. Okay. So when we're talking about infinite and finite sets, one of the sets, the first sets that you ever learned anything about when you were a kid in preschool was the natural numbers. What does anybody know what the natural numbers are? It's okay to guess. Yeah, the natural way you learn to count, right? That's how we learn to count, and we call those the mathematicians call those the natural numbers. The natural numbers start with 1, 2, 3, 4, keep going on forever. Okay, it keeps going to infinity, but it's the counting numbers. Is that an infinite set or a finite set? Infinite because it doesn't do what? Doesn't stop. It keeps going, right? Every time we think we got to the end, we just add one more and we got another number. So the natural numbers is a good example of an infinite set. Okay, we know what numbers are in it, but we know it doesn't stop. It keeps going forever. So there's a set that's infinite out of that. A finite set could be a subset of the natural numbers. Example might be 7, 8, 9, and then it puts the dot, 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 and maybe stops at 15. The dot, dot, dot in the middle means continue the pattern until you get to this number. That is a finite set because it has a set number, a limited number of elements. 7, 8, 9, 10, 11, 12, 13, 14, and 15. It's got 9 elements in it, and that's it. Nothing else. Okay? So we see an infinite set keeps going forever. A finite set is going to have a stopping place. And we can see through these examples right here that how it's going to look. They might not put as many dots there. They may put only 3 there, but I like to put more just because it looks better. Okay. So finite sets end, infinite sets don't. Another way that a finite set might be written would be curly braces, and they might use an inequality. What does this inequality right here say X is?
X is greater than 9, but it's less than 13.
Okay, X is greater than 9 or less than 13. What's the little bar underneath the inequality symbol mean? Or equal to. So it could be 9, it could be 13, but all of the X's that we're talking about are between those two numbers, from 9 to 13. So that would be an infinite or a finite set. It'd be finite because it's got a starting and an ending point, right? A finite set. So idea here is to look at a set and be able to determine, is it infinite or finite? If it doesn't have an end, infinite. If it has an end, finite. That's the difference in those two. So being able to do that. Now, let's take some sets that are described in words and try to list the elements in those sets. So these are actually going to be lettered. I like to letter my examples that we're actually doing work on. So I'll start with letter A and keep going from there. Sometimes I just I'll add an extra example or take away one that I don't think we need to do because it seems like everybody understands it from my notes. So I may have to ask you what letter we're on sometimes, just because I change up from what's written here on my my notes that I've done. But the idea here is we are going to follow the instructions to list the elements in each set. All right, so that's the instructions. The first problem is a set of x's that x is a natural number less than 7. So we want to list out the numbers that are in that set. So we're going to write a set that's actually the numbers that fit that description. So what are the natural numbers that are less than 7? 1, 2, 3, 4, 5, 6. Is 7 included? No, because it said less than 7. It didn't say equal to. So we have to leave out the 7. So 1 through 6 are the natural numbers that are less than 7. Okay. Yes, ma'am.
So whenever we're doing a problem, for you, say on Canvas, or if we're having to write something out, can we put 1 ... 6, or do we have to put 1 back?
On Canvas, it's going to be it's going to have like a multiple choice type situation. On a lab, I'll kind of explain it as we get to each problem on the lab. I'll kind of tell you how you would write your answer on that. It'd be easier to explain once you got one in your hands as far as that goes. Good questions, though. All right, let's do another one here. All x's such that x is a natural number less than 20 and a multiple of 3. What's it mean to be a multiple of 3? Math word there. Say it again. Not will go into 3, but I think you know what you mean there. 3 will go into it. Yeah, that's what you mean. So anything that 3 divides into evenly, but it's also got to be less than 20. So let's think about the natural numbers that are less than 20. So we got 1 through 19. Which one of those go? Does 3 divide into evenly? Obviously 3. What else? 6, 9, 12, 18. One in between there. 15. So there's a finite set that we have there. All right. So listing the elements that are in the set, not anything just incredibly hard there, just good old-fashioned set stuff. All right, now let's get into a little bit of set definitions here. So these are just definitions here. The universal set, same section, and then the null set. All right. The universal set in general is everything in a discussion or problem, for our sake. Many times they will define the universal set using the letter U. They will say U, and it'll have a problem or maybe a set of problems, and it'll say U, and it'll give you what the universal set is for that particular set of problems. Sometimes it might be the natural numbers. Sometimes it might be the numbers 1 through 20, depending on the situation. But it's everything that's in the discussion is the universal set. The null set is the empty set. It's the opposite of the universal set. The null set is the empty set. You will hear me mix those two words up all the time. I was raised calling it the empty set, and then the verbiage changed, and they wanted to just call it the null set. But they're the same thing. They mean the same thing. So empty set, null set are the same thing. So if you hear me say empty set, I meant the null set. If you hear me say null set, I meant the empty set. Okay. If it's empty, what kind of elements does it have? Does it have any? No, it doesn't have any elements. So it has no elements. Okay. It has a notation of the curly braces, just empty. That's the empty set. That makes sense, right? That seems to be logical. Or a circle with a slash through it. And you may have seen that notation before when you're solving an equation and it didn't have an answer. You could use that symbol, no solution. It just meant the empty set. The null set, the empty set, either of those notations are the same thing. So our textbook tends to bounce back and use both of them. It's not, so that's why I show both of them. It will sometimes use the circle with the slash when it means the null set. It will sometimes use the empty braces when it's talking about that. But those two mean the same things. They both are the null set. Okay. All right. Another definition, real quick, is a subset. A subset, a smaller group of elements from a larger set. That makes sense, right? Smaller group of elements from a larger set. A subset is just a smaller group, okay, from that. And there's things called a proper subset. A proper subset, and not if you ever get into set theory, proper subset just means it has to be smaller than it. Like it's completely smaller. Technically, every set is a subset of itself. Is one of the rules for set theory. But a proper subset just means if it's got 5 elements in it, a subset has to have 4 or less. A proper subset does. Not that you have to know that for Math 100, but if you ever were to Google sets or set theory, you're going to run into some things that seem obvious that are not really that obvious as far as that goes. So let's look at an example of a set and then another set and talk about subset for just a second. Example C. Set A. Let's just do the numbers 1 through 8 is what I'm doing here. 1, 2, 3, 4, 5, 6, 7, 8. Numbers 1 through 8. Set B, 2, 5, and 7. We have 2 sets there. The question we want to answer is B a subset of A? Every element that's in B was in A. So B is a subset of that. There is notation for that. Okay. That's okay. That's quite okay. I enjoy folks that want to answer. That helps me because it gets boring when hearing my own voice. So B is a subset of A. The way you make that notation is like this. It looks like a C with a line underneath it. It's kind of like what it looks like. That means B is a subset of A. That's the notation for that. B is a subset of A. That's how you read that. B is a subset of A. So not terribly hard there. Let's look at another example. Same idea though. We're talking about subsets. So set A, that same set, 1 through 8. I'm writing the numbers in order. Technically, it doesn't matter if they're in order or not. They can still be part of that set if they're not in order. Set C, or let's call it set D instead of set C, because the notation gets kind of crazy. Curly brace, 10, 15, and 4. Notice those are not in order. Is D a subset of A? No. Why not? Yeah, every element that's in D is not an A. Some of them are, but it's not every one of them. So that means it's not a subset. So you could write D subset of A and then put a line through it. That's the notation for not a subset. We're just answering that question there. But subsets are have to have every element in a subset has to be in the original set that you're trying to be a subset of. Okay. All right. Does anybody remember doing what was called Venn diagrams? Does that bring up any, I would say, pleasant memories in math class, but it may not be a pleasant memory. I don't know. Maybe you don't remember the name of it, but you remember this picture. I remember doing those at some point in life. We've done those. My son in second grade came home with one of these the other day for some story that they were reading in class, and I thought, hey, awesome! They're doing some math in the second grade. They don't do a whole lot of math in the second grade, but they did it with English stuff. I'm not a big English fan, but you got to do that stuff. So it's important that they learn that. All right. So if we've got a couple of sets, and we're going to have set A, and I'm going to get some numbers here: 3, 5, 7, 9, 11, and 13. And set B, 6, 8, 10, 11, 13, and 14. And we're going to put that into this Venn diagram. Okay. The way Venn diagrams work, the little football shape in the middle, what goes in there? Numbers that are in both. Okay. So when we look at our sets, what numbers are in both set A and set B? 11 and 13. Okay. Over here in this 3/4 moon right here should be the elements that are in A that are not in B. Okay. So elements in A, 3, 5, 7, 9, 11, and 13 are in A. They're all in the A circle. So I've got the A circle finished. Got all my elements in there. And then the B circle, I've already put down 11 and 13. They're in the B circle. I need to put everything else. 6, 8, 10, and 14. So we've taken a couple of sets and placed it into the Venn diagram. This area in the middle, that football shape, is called the intersection of set A and B. The notation for intersection, A intersects B, the set is 11 and 13. So the intersection notation is like an upside down U shape. That's intersection. Okay. Intersection, it's in both. It's an and. Intersection is and. Okay. Intersection, think and. A union in set theory is an or. Okay. So when we talk about a union, it's a complete list of all elements in both sets. So when we talk about A union B, so the union is is a U. Makes sense, right? It's the everybody that's in the Venn diagram all together that's in both sets. Okay. We only list the number once if it's in there. So we got 3, 5, 6, 7, 8, 9, 10, 11, 13, and 14. That's the union of set A and B from our example. Notice 11 and 13 are only listed once. They were in both sets, but we only list them once. I put it in order. Again, order technically does not matter. It just makes me feel less apprehensive when it's in order. Okay, and that's the way you're probably going to see it most times if you check answers in the back of the book. So intersection, it's the overlap. It's where they're in this set and another set. Union is all inclusive, everybody in the pool. Okay, so know the difference in those two things. All right, let's take a couple of sets and find the intersections and unions of them. Bless you. Set W, some numbers 9, 15, 25, and 36. Set X, 15, 20, 25, 30, and 35. Question 1, W intersect X. And question 2, W union X. And technically, it doesn't matter what order you put the W or the X. It should be the same set no matter what. All right, so the intersection. What numbers are in both sets? 15 and 25. It's that easy, folks. This is not rocket science. Not even, I wouldn't call this algebra yet. We're just doing some set stuff. So we're not even doing any algebra. The union, what's the union do again? Everything. Everybody that's in both sets. So I'm going to list out 9, 15, 20, 25, 30, 35, and then 36. Nothing crazy about that. All right. One more little example involving that stuff. Set G is 1, 3, and 5. Set H, let's do 2, 4, and 6. G intersect H. That's what we want to answer. What's in both of them? Nothing, right? So if there's nothing there, it's the what? It's the empty set, the null set. So either the empty curly braces or the circle with the slash through it. I'll take either one of those answers. Okay. Know that they mean the same things. Okay. You may see empty braces or the circle with the slash through it on any assignment. They mean the same thing, so we need to know both notations for that. Okay, so empty set, null set, when there's no intersection, when nothing overlaps. All right, easy thing there, not very hard at all. All right. Next thing, definition. Complement with an E, not an I. Complement of a set. Elements from the universal set. And I say universal, it may just be a larger set that are not in the given set. Okay. Complement of a set, the notation. So let's, the notation is an apostrophe kind of, they call it a prime mark in math, but it's kind of like an apostrophe. C prime would be C complement. That's the idea of that. So C prime. That means the complement of C. All right, so let's look at an example that really make sense. Doesn't really make sense till you see an example. So the universal set, we'll call it U, numbers 1 through 7. 1, 2, 3, 4, 5, 6, 7. Set A, we're gonna say it's 1, 3, 5, and 7. So it's the odd numbers that are in there. Set B, let's do 3, 4, and 6. Let's do, all right, so the universal set is the one we're working from, okay? It's the larger set that we're talking about the complement from. So A complement, or A prime. What numbers from U are elements of A prime? All right, so A has 1, 3, 5, and 7 in it. What are the numbers that are in U that are not 1, 3, 5, and 7? 2, 4, and 6. That's what a complement means. Okay, it's the things that are not in set A that are in the universal set. Okay. If we talk about B prime or B complement, B has 3, 4, and 6 in it. So what are the numbers in the universal set that are not in B? 1, 2, 5, and 7. Yeah. There we got the idea. Curly braces, not looking like a curly brace. There we go. Okay. 1, 2, 5, and 7 are the complement of that. Okay. While we're here, let's just tie up loose ends on the intersections and union. Let's do intersection of A intersect B. What's in there? Just 3. It's a set with the number 3 in it. That's it. Set A intersects B at the number 3. That's it. That's the only thing that's in there. All right. All right. So a lot of set theory there. Nothing, not a lot of algebra, no calculations or anything like that, but a lot of set theory. So we're going to take that and move into section 2 and talk about R.2. We're going to talk about the real numbers. And their properties. All right, so the real number system is where we spend a lot of our time in Math 100 and 110, but we do get into the complex number systems so a little bit. So when we talk about this, I'm going to bring up the complex number system. The complex number system is the largest set that we deal with in algebra. Okay, the complex number system is the biggest bucket of numbers that we deal with. Okay, so when I talk about the number system, I like to think about it as buckets that sit inside of buckets. So you've got this big box, and it's a big square, like a big swimming pool. Okay, that big box is the complex numbers. Okay, the complex numbers include like the i's. Remember in algebra in high school, you took the square root of a negative number. You like the square root of -4 was 2i. Y'all remember doing that? You had 2i, and like I squared is equal to -1. That sort of stuff. That's what the complex numbers encloses. Okay, so the complex numbers is the biggest picture we've got. Inside of the complex numbers, you've got a portion of that is the real numbers. So it's kind of like we drop a wall inside the pool, and this box over here is the real numbers. Over here, you've got just the imaginary parts like 2i and -3i and I squared, I to the third power, and that sort of stuff is over there. I radical 6, stuff like that. That's what examples of numbers that would be out there. The real numbers is where we spend most of our time in any kind of math classes, with the real number system. And that's where we're going to start out in Math 100. The real number system has buckets inside of that. So inside of the real number system, there's this bucket that kind of sits over here by itself. And it's the irrational numbers. The irrational numbers are numbers that cannot be written as fractions. Okay? Irrational numbers are numbers that cannot be written as fractions. Examples would be like the square root of 3. Pi is a number that's a irrational number. Square root of 7, square root of 22, stuff like that. Things that don't work out real nice. The decimals don't repeat and they don't terminate. They don't stop. Okay? So that's an irrational number. It can't be written as a fraction. It's kind of this separate bucket over here. It doesn't. The only bucket it sits inside of is the real numbers. Okay, so it's sitting over here on that side of the pool. Over here on the other side, we got this large bucket. That larger bucket is the rational numbers. The rational numbers, that means numbers that can be written as fractions. Okay. Most numbers can be written as fractions. We think about, the number 7. 7 over 1 is a fraction. So that's an example of a rational number. Another rational number would be like 2/3. That's already a fraction. I have to work real hard at that. So rational numbers are numbers that can be written as fractions. They're terminating decimals, 0.25. They're repeating decimals, 0.3 repeating. It's the same thing as 1/3. That bucket is the largest bucket in the real number system. Okay, so in the real numbers, you got the rational numbers sitting in there. Inside of that bucket is a smaller bucket that sits inside of that one, and it's called the integers. Inside of the integer bucket is a smaller bucket yet. It's called the whole numbers. And inside of the whole numbers is another smaller bucket, and that's where those natural numbers that we've already worked with live. Okay? So the natural numbers, because they're set inside of this bucket, remember what are the natural numbers again? 1, 2, 3, the counting numbers, the things we learned counting, right? So they're set inside of this bucket. So the natural numbers are also a whole number. What else is a whole number? What adds to the group of whole numbers? Does anybody know? We got the counting numbers 1, 2, 3, 4, 5 to infinity. The whole numbers, the only other number that adds to that, 0. Okay, so 0 adds to that. So the natural numbers, you got 1, 2, carry on. The whole numbers, put a 0 in there and adds to it. So the whole number bucket it's got 0 set in here, and then it's got all of the natural numbers in it too. So if you're a natural number, you're automatically a whole number. If you're a whole number, what bucket are you setting inside of? Integers. What are the integers? So we got whole numbers that are 0, 1, 2, 3, 4, 5, 6, keep going. What does integers add to the game?
Like 1.5.
No. That's absolute value. Integers. What kind of numbers are integers? Negative and whole numbers. The negative natural numbers is what the integers adds to the game. So we got -1, -2, -3. No decimals, no fractions yet, but the negative numbers. So we got -1 or negative infinity, -3, -2, -1. Keep going from there, okay? The rational numbers, that's where the fractions and the decimals come in. So here's what happens. You're set inside of the natural numbers. If you're the number 5, you're a natural number, but you're also a whole number. But you're also an integer, but you're also a rational number. Because you can write 5 as a fraction, right? 5 over 1, 50 over 10. A lot of different ways to write 5 as a fraction. But you're a rational number, you're an integer, you're a whole number, and your innermost being, at the root of things, you're a natural number. But because you sit inside all these other buckets, you get all of that as well, okay? And you're a real number, okay? So the number system, the way it works there is you get natural numbers, the smaller set we have. Whole numbers just adds a 0 to it, so it doesn't take much more room. And then the integers, we get all those negatives. And then the rational numbers, we get the negatives, 0, all the counting numbers, plus decimals and fractions that terminate or repeat. After we get outside of that, we got the irrational numbers. Those are the decimals that don't repeat and don't terminate. And that makes up the real number system. Okay, so those are the numbers that we're dealing with here. Now, each one of those has a abbreviation for that. So the irrational numbers, irrational, that's a capital I. The rational, that's a Q. It doesn't make sense to think about rational. Rational numbers are fractions. Fractions is what operation? What math operation? Divide. What's that name of an answer to a division block? I remember that word. That's exactly right. Yeah, it's the quotient. So quotient starts with Q, so it makes sense that rational is the Q. Now that R is already taken by real. That's the reason it didn't get it. Okay, so irrationals gets an I, rationals gets a Q, and then inside of the rationals you have an integer. And integers, ER is after the G. Integers, I is already taken, so we can't use that again. So we're going to use a Z. That one I don't understand. I don't know why. I took a math history class in college. Yeah, it sounds like it's as much fun as it sounds like it was. But we didn't get to that part. I assume that there's some Greek word or something that starts with Z that means integer. I don't know. If you find that out, shoot me a link on Google so that I can know the answer to that. I've never been curious enough to really research it much. So we got integers. Inside of integers, you got whole numbers. Whole numbers is a W. And inside of whole numbers, you got natural numbers. And there we use an N. Okay. And we'll go ahead and put real in an R. Okay. So that's our abbreviations that we'll use as we're classifying numbers here based on what they are. Okay. So natural numbers, whole numbers, integers, rational numbers, irrationals, and reals. Okay, so what we're going to do is we're going to take a set. So here's our set, A, and I'm just going to pick some numbers, -8, -6, -12 over 4, 0, 1/2, square root of 2, square root of 5, and 6. So those are the numbers that are in my set A. And then I want to list the subsets that are natural numbers. And so we'll start with the natural numbers. What's the subset of that set of numbers that are natural? Six would be a natural number. Anything else? 0 is a whole number, so that doesn't count. 1/2's a fraction. That can't be it. Square root of 2, that's not it. Square root of 5, that can't be it. So 6 is the only thing. So our natural number set is the number 6. That's the only thing in there. Good to know. Let's do the whole numbers. We'll just ease our way out of the buckets. What's a whole number? Natural numbers plus 0. So if 6 was a natural number, does it have to be a whole number? Yeah. So my set, it's got to have a 6 in it, but what else is there? 0. It's in our set, so it's a whole number. So natural numbers plus 0, that's the whole numbers. Okay, so we get 0 and 6. That's our whole number set, the subset of set A. All right. Next step out into the buckets is the integers. So let's get some integers. I'll erase my curly braces. Curly brace rider is not working tonight. It's a long day. All right, so integers, it's the whole numbers plus the negative numbers. Okay, so 0 and 6. And what else? Negative 8, negative 6, 0, and 6. Why did he leave a blank right there? 3 times, right? It goes even. That one there, it's a fraction, but it reduces to be a nice integer. So, hey, there's a little bit of a calculation to do there. Negative 12 divided by 4 is negative 3. So that's an integer as well, even though it's kind of in disguise. And that's one of the things that they'll kind of try to do to you here is put some numbers in disguise and say, hey, it may not look like an integer, but it works out to be one. So be careful of that. Okay. Now I'll go to the rational numbers. Q. Yes. Yes, that's right. Because rational numbers, remember, it's the bigger bucket, and if you're an integer, you're inside the rational number too. So you get both of them out of that. Okay. So what else? What do we add to this? The integer group to put into the rational number group. 1/2. So it's everything we already had. Negative 8, negative 6, negative 12 over 4, 0, and then we add the 1/2 in there because it's a fraction. And we get the rational numbers as well. Okay. And then irrational numbers. Let's get that set. Which numbers are irrational? Square root of 2 and the square root of 5. If you try to calculate those, the decimal never repeats and it never ends. It keeps going. Your calculator, if you type that in there, it's going to give you all the digits it can. But if you go to Google and type it in there, it's going to give you even more digits. And so irrational numbers, square root of 2 and square root of 5 are irrational out of that set. Irrational means you can't write it as a fraction. The decimal never repeats and it never terminates. That's what irrational numbers do. Okay. Not bad. Not bad. All right. Let's actually get into doing a little bit of math tonight and do same section. It's weird that it's all together, but it's part of that real number properties. And when we're dealing with real numbers, we deal with operations. And we deal with operations in math. We do order of operations. So we're going to review that as we go here. So order of operations. What should always come first in order of operations? Parentheses. We call them parentheses. Any kind of grouping symbol, though, comes first. If it's parentheses like normal, or a square bracket, or even an absolute value mark. Absolute value marks have the same rank in order of operations as parentheses. So if you see absolute value marks, that's a grouping symbol. So that's going to come first. So if there are any parentheses, we want to do the work that's inside of those first. After that, we do what? Exponents. After exponents, multiply and divide. Do we always do multiplication before division? No. How do we do that? Whichever one comes first in the problem as you read it left to right. So multiplication to division, technically they rank the same, so whichever one, as you read the problem left to right, whichever one comes first is the one you're going to do. And then last, you add and subtract. Same rule. Whichever one comes first, left to right, is the order that you do that. Adding doesn't go in front of subtraction always. Depends on what order they're in, left to right in the problem. So as we're doing problems, we need to follow order of operations. So we will try to do that as we go here. So now, exponents, when we're evaluating exponents, just a review here of some terminology when I say something so that you know. When you're doing exponents, you got A with an exponent of n. This A is called the base, and the n is the exponent. So if I say the word base, I'm talking about that big number at the bottom. So when I talk about example B here, 4 to the third power, the base is 4, the exponent is 3. So when I say base, I'm talking about that 4. So a base of a 4, exponent of a 3. What does it mean to say 4 to the third power? Yeah, 4 times 4 times 4. And we can do that math. 4 times 4 is 16. 16 times 4, 10 times 4 is 40. 4 times 6 is 24. Add those together, get 64. With the graphing calculator, I'm going to kind of show you as we go here. A lot of you don't have that yet, but I'm going to have it on the video here so that you can see it. If you're going to evaluate an exponent with the calculator, if I need to do 4 to the third power or 4 to any power, I'm going to type the base, 4, and then over here on the right-hand side, right above the division symbol, looks like a little house top. It's called the caret symbol. That gets you an exponent, okay? So exponent, and then the TI-84 is going to show a picture like that. You type in whatever exponent you need. I'm going to put a 3 and hit enter, and there I get my answer out of it. So that's how the graphing calculator works with that. You may not be as familiar with that. I will go ahead and tell you, don't get in the habit of using your phone as a calculator because I just can't do that. Phones can do too much. There's photo math. You may know about that app. If you don't, you do now. It's a phenomenal app. It really can help you work a problem, but it doesn't. It just you can't do that. So get you a calculator. Don't get an app for your phone. I've had people ask about that before. It's too insecure because your phone can communicate with the internet and other people, where a graphing calculator at this point cannot. Maybe in the future they do that. I hope not, because it just really complicates things if they do. But so go ahead and get that calculator and see if you can get used to that. Let's do a negative number to an exponent. So when we square -6, what does that mean? Well, it means -6 times -6, and we know that negative times a negative is positive, and it should be positive 36. I want to show you a pitfall of the graphing calculator that a lot of people fall into. When a lot of people do this problem on the graphing calculator, they'll just go -6 raised to the second power and hit enter. What did it give me back? the wrong answer. It's not negative 36. We know it should be positive 36, right? We just did that. Here's what your calculator reads. When it reads this column, it says negative sign and then square 6. And in order of operations, squaring 6 comes before putting a negative in front, right? So it doesn't read this as negative 6 squared. It reads it as negative times 6 squared, which is not the same thing. So what you have to do is either A, know that when you square something, you always get a positive answer, or B, put it in right. Negative 6 in parentheses raised to the second power. And then that says, oh, you're taking a negative 6 and squaring it. That's what that reads it that way. So that's one of the differences when you go to the graphing calculator. A lot of my high school students really struggle with that because they're so used to the little scientifics, and they kind of infer things for you. With the graphing calculator, it's very it follows the rules exactly. How you type it in is what it's going to do. So you've got to be careful of that. As we're going, we'll learn some growing pains that go with using the graphing calculator and how we got to get used to it. All right, let's go ahead and get into evaluating. So this is where we're actually doing order of operations. We've kind of reviewed the exponent stuff, and we know how to do that sort of thing with the calculator. So let's evaluate some expressions using order of operations. So example D, 4 times 3 in parentheses squared plus 6 divided by 3. In this problem, what should come first? Parentheses. 4 times 3 is 12. What should happen next? Your exponent. So we're squaring 12. What's 12 squared? Does anybody know? 144. What should happen next? Division. What are we dividing? 6 divided by 3. Okay. Most common. I don't know if you guys see this on social media, but I see these problems that come up on social media. It's an order of operations problem, and I can't say anything to him because it wouldn't be right because he's older than me and probably smarter than me, but not at this stuff. But anyway, everybody always misses it because they'll do 144 plus 6 and then divide that answer by 3. That's what always seems to happen on those problems. But you guys are right. You divide 6 by the 3 and then do your addition. So 144 plus 2 is 146. You got the answer. Okay, so doing it by hand, one step at a time, that's wonderful, that's great, but who does that? Nobody. Okay, so most of us are going to go to their calculator, and if we can type it in like it's written without messing up, okay, so I've typed in 4 times 3 in parentheses, and then I did the exponent thing and put the 2 up there, but it's still in the exponent. So with the graphing calculator, to get out of the exponent, you got to press the right arrow key, and it just drops you back down to earth, plus 6, and then divided by 3. So instead of writing an old school division symbol, just use a slash. Okay? And this should get us the same exact answer as what we did by doing it step by step. So I hit enter. That's how most of us do things, or have been doing them for quite a while. I try to break my high school kids from relying so much on the calculator. But you guys, I think, we're at this point, we're trying to get college credits, and I'm trying to get them to think a little bit more on those things, because I'm trying to get somewhere else and I don't want to use calculator too much. So I like doing it by hand, but I'm fine with using the calculator. Not going to hurt my feelings at all. Okay. So, but make sure you can type it in right. That's going to be a learning curve as you get that graphing calculator and get used to it. Okay. Let's do this one. 6 divided by 3 times 2 to the third times 5. That's a weird one that can trip some folks up sometimes. 6 divided by 3 times 2 to the third plus or times 5. That was weird because it doesn't have an addition or a subtraction problem to kind of separate it. What should happen first, technically?
2 to the third.
2 to the third power should happen first. So 2 to the third would be 2 times 2 times 2, which is, try again. 2 times 2 is 4, times 2 is 8. Now, what part of that goes next? 6 divided by 3. I thought multiplication came before addition. No, it's left to right. So 6 divided by 3 is 2. 2 times 8 is 16 times 5. 50 plus 30 is 8. And this is one that I think I did actually steal from Facebook. Or one of those Facebook things where everybody they went and did this. They did 3 times 8 times 5 and then divided 6 by that. Everybody was wrong. A lot of people got it wrong because they did this multiplication first because they remembered, please excuse my dear Aunt Sally, and they thought multiplication had to come before division. And you guys know better, and you did a good job. I'm proud of you. Way to go. You can win at Facebook if you do that. Nobody does Facebook anymore. Instagram, whatever you do. All right, what letter are we on here? F. Four plus 3 squared over 6 minus 5 times 3. So these are intimidating, but not hard. Go through these with some of my high school students this week. We were doing, or actually last week, we just started schooling in Gary County, so we're about 3 weeks behind everybody else. So we're kind of trying to get them back in the swing of things. So we started going over these, and I was trying to get them to do things without the calculator that first week, just to get their brain going on math. And everybody was intimidated by this problem because it looks like a fraction. But the math in it's not that hard. What's the first thing that happens? Exponents. 3 squared is, it's 9. We know that 4 plus 9 is on the top. And on the bottom, we got 6 minus 5 times 3, which is 15. So it's almost you just take the top part, work it as one problem, take the bottom part, work it as another problem, and then do your division. So what's 4 plus 9? 13. And on the bottom, 6 minus 15. This is where everybody had a problem, or not everybody, but some of my high school students had a problem with that. There's a problem like this. 6 minus 15.
-9.
-9 is what it should be. So if I've got $6 and I in my checking account and I pay for something that's 15, now I have -$9. You take my I'm probably going to have -$39. But -9 there. 6 minus 15. Think about it. 15 minus 6 is 9. 15 was bigger, so it's negative. So that's how it's -9. 13 over 9 reduce. 13 is prime. 9 is divisible by 3. But 3 doesn't go into 13, so we leave it as that fraction, negative. If you put the negative out in front like this, that's how you normally see it. If you put the negative with 13 in the top, that's fine too. They're all the same, no matter where the negative is at, as long as there's only one of them. Okay, so I'm okay with ever how you do that. I generally most folks do it this second way there. That's just how most folks write it. It's not necessarily wrong either way. All right. Excuse me. All right, let's make it look more like algebra. Let's put some variables in there. Example G. The instructions will usually say evaluate, but we know that just means work it out, get the answer. That's all that means. And maybe they got -4x² minus 7y plus 4z. We want to evaluate that for x equals -2, y equals 5, z equals -3. We're going to evaluate this expression given what the variables stand for. So this looks more like algebra. What do we do first? Plug in the numbers. Put the numbers in the place of the variables. So we got -4, and anytime I'm doing that, I'm going to put parentheses around the number that I'm plugging in. That's a great habit to get into. I know it's an extra writing. So plug those in. Put those parentheses in there. It'll save you the headache, especially if you're going to go and type that into the calculator. Parentheses are all extra parentheses. You don't cause problems. Lack of parentheses can cause problems. So be careful of that. So I'm going to work this out. What do I do first? Exponents. So -2 squared should be 4. So I got -4 and 4, and then 7 and 5, 4 and -3. So that I can do all of those at the same time, right? Because they're all multiplication problems. And then put it all together. So 4 times -4 would be, yeah, you guys know that. Minus 7 times 5, 35, plus 4 times -3. So that'd be plus -12, okay? And then I'm just putting that all together. -16 minus 35. So if I've got a negative number and I subtract from it, it's going to get more negative. So I'm going to total those two up. That'd be 51. Is that right? -51. And then a -12 added to that is going to make it more negative. It would be -63, I hope. If you want to type it into the calculator here at this blue step, I'm fine with that. It's not going to hurt my feelings at all. Okay? Just know how to plug it in and put things in the right spot. Parentheses are your friend. Okay? Make sure that you're not shy about using parentheses. Okay? Let's do another one of those evaluation problems. What letter are we on? H? Yep. 2 parentheses x minus 5 squared plus 4y over z plus 4. And I'm going to use the same variable values that we used in the first one. Okay. Same values for x, y, and z. Again, a lot of people get intimidated by a problem like this because it looks like a big fraction, and I think it's really hard. But actually, the math in it is not very hard at all. So we want to plug in and work out. That's all we got to do. 2, and then we got -2 minus 5 plus 4 times 5 over -3 plus 4. So as I work that out, -2 minus 5 would be what? -7. So we have -7 squared. And I'm going to go ahead and multiply 4 times 5 because it's not going to be affected by that. And I'm going to go ahead and add -3 and 4. So I'm just doing a few steps at once here that I know are not going to be affected by other steps. When I square -7, what do I get? 49. And 49 times 2 would be 98 plus 20. If it was 100, it'd be 120. So you take 2 away from that, you get 118. Divided by 1. That's easy math. 118. Again, I'm okay with using calculator to do that and help you get that right. Just understand how you need to type that in so that you're not messing some things up there. All right. Let's look at simplifying an expression. It's kind of in the same area. It's in the same section. Simplify. When you hear the word simplify, what does that tell you? Break it down or put what together? For the Wheel of Fortune board, we have 2 blanks, both with one with 4 letters, one with 5 letters. Vanna would press the button, and an L would come up in the first box. Like terms, that's exactly right. So like, when you see simplify, you want to think like terms. That's what the name of the game that we're looking for here. So like terms. Like terms. What letter are we on here? I. Simplify. So that means put like terms together. So maybe like 6 plus x plus 9 minus 4x. Nice little problem there. Like terms go together. That's what we got to do. So what's in front of this x that's right here? It's understood 1 to be there. Okay, so it's a 1x. Okay, and 1x and negative 4x together would be negative 3x. Okay, we're not crossing an equal sign, so you don't use the opposite. That's the most common mistake when we're doing this stuff is a lot of folks want to say, oh, you add 4x to the 1x. No, it's 1x and negative 4x putting together. You're not crossing an equal sign, so you don't change the sign of anything. Okay, so 1x and negative 4x is negative 3x. 6 plus 9 plus 14. I put the variable stuff in the front. That's the way you're going to have to do it later on. So if you'll go ahead and get in that habit now, you won't have to redo it. Yes, sir. It should be 15. You're right. As soon as you started to say something, I was like, that's not 14, it's 15. 9 plus 6 is 15. Thank you. All right. So put the variable stuff in the front. If there's more than one variable, it doesn't matter what order you put the variables in, but you should usually put the variable stuff toward the front because we're going to have to do that later on. Let's do this one. 7 minus 2 plus 3x plus 5x minus 10. There's some parentheses thrown in there to try and distract you. But we know those parentheses don't really matter on this problem. We're just going to work on the inside first, though, right? So 7 minus 2 would be 5. And then we can put the like terms together from there. X's, how many X's we got? 8. And then 5 minus 10, negative 5. And there we have the simplified version of that problem. Nothing extremely dangerous about that. Pretty easy thing to do, right? So simplifying, putting like terms together. That's the key to that stuff. All right. All right. Let's do 7:30. You guys need a break, or are you good? We got 2 sections left. One is pretty short, and the other one is not as short. So you tell me. If you need a break, we'll take about a 10-minute break and let you go splash some water on your face or get you a drink or something like that. If you need to go to the restroom while we're do in class, you can go take care of that. You don't have to get permission from me or anything. Just know that I'm gonna keep going while you're gone, and so you just catch up as you come in. All right, so we'll just keep going then, since you guys. I'm fine with keeping going and getting out here a little earlier. All right, so let's do section R3. Let's talk about polynomials. Just a second here. All right, polynomials. When we talk about polynomials, we'll first need to talk about the rules of exponents. We'll review those real quick. So the product rule, not that you have to know the name of the rule, but product is what kind of math problem? Multiplying, okay? What's the rule for exponents? So like a to the m times a to the n. The base is the same. If the bases are the same and you're multiplying, the rule is that you add the exponents. An example of that would be like x to the third power times x to the fifth power. The answer would be x to the eighth power. Bases are the same, so you add the exponents. So remember, anytime you're multiplying and the bases are the same, you're going to add exponents. Product rule. Okay? The power rule. Power rule means you have a base with an exponent in parentheses with an exponent outside. The rule is that you multiply the exponents. An example of that would be like x to the sixth power and then squared. What's 6 times 2? 12. So it would end up being x to the 12th power. Okay. So the power rule, anytime you see parentheses with an exponent outside and just something in there, you're going to multiply your exponents. Okay. Another variation of the power rule is if you have more than one thing in the parentheses that's a different base. So like a to the m, b to the n, and it's all to the x power. It's like distributed property, a to the mx, b to the nx. Example, x squared, y to the third, all to the fourth power. That would be x to the eighth, y to the 12th. That's a small example of that. Okay. So if there's more than one thing multiplied together on the inside of the parentheses, everybody gets the exponents on the outside multiplied to them. Okay. Another variation of the power rule is a fraction on the inside. I don't think this will come up much in this section, but it does come up some in the course. Again, you've got different bases on top and bottom. It still multiplies the exponents everywhere by that one on the outside. So that a to the mx over b to the nx. An example of that might be x to the fourth power over y to the third power, all to the fifth. That works out to be x to the 20th over y to the 15th. It's an example of that. Okay, the power rule just says anytime there's parentheses, an exponent on the outside, multiplying the exponents is the way to go. All right, parentheses is the key to the power rule. All right, last rule is the quotient rule. Quotient, remember, is what kind of problem? Division problem. And if you add when you multiply, what do you do when you divide? You do the opposite, right? A to the m over a to the n. You subtract your exponents. The bases have to be the same for that to happen. So an example of that might be x to the 13th over x to the 7th. The answer to that would be x to the 13 minus 7 is 6 out of that. So the subtract is the rule for that one. So, Very, very easy stuff there. Okay, so exponent rules, just reviewing those for us to use a little bit here in this section. All right, so let's do some examples of some exponent rules and mixing in some just regular multiplication with that. So the instructions would be simplify. We're not necessarily looking for like terms here. We're looking for like bases so that we can do those exponent rules with this. We're not trying to combine like terms. We're just trying to work out the math problem to get as much together as we can. So example A for this section, let's say we had y to the 6th times y to the 5th. Real simple one to start off with. Is the base the same? Yeah, they're both y's and they're multiplying. So the rule is you do what with the exponents? Add them. So it'd be y to the 11th. Real simple, real easy, real boring. What if you put a number in front of those? So like 3x to the 3rd, bless you, times 4x to the 5th. What do you do with the 3 and the 4 that are in the front? Yeah, it's multiplication problem, isn't it? You just multiply. 3 times 4 is 12. And then you do the product rule with the variables. Be x to the what? 8. Yeah, real simple. I've done this before. May have been a while. May not have been great at it when you did it before. Hopefully we get better at it this time. Okay. Let's step it up a notch. Put 3 things there. 6x to the 5th. 9x to the 3rd. And 1/2 x squared. Ooh, you put a fraction in there. Does it matter what order I multiply things together at? No. Multiplication, the name of the property that allows you to do it in any order you want to is the commutative property. So if I want to take half of 6 first, I can do that. I don't have to say 6 times 9 and then take half of a larger number. I can take half of 6 at the beginning. What's half of 6? 3. What's 3 times 9? 27. That wasn't too bad. If I had done it in order 6 times 9, that's 72. What's half of 72? I know that, but not everybody is got that quick. But a half of 6, everybody had that. Y'all knew that. So taking shortcuts there can help you, knowing that you can do it in a different order can make the problem much easier. So that's how we do it. And our variable is x. Everybody is an x, so the bases are the same. What do we do with our exponents? Add them up. 5 plus 3 plus 2 would be 10, right? 8 plus 2, or 5 plus 5. 27x to the 10th. Not too bad. Example D over here on the edge. We don't need much room for this one. It's a short one. X to the 5th squared. What do you do with those exponents? Times them. The x to the 10th. There you go. Short and easy one. Let's say we had, example E, 2 to the 3rd, x to the 4th. And that is all in parentheses, raised to the 3rd power. What should I do with the exponents? Okay, I could work that out and get what? Okay, so I got 2 different ways to do that. She said I could work out 2 to the 3rd and get 8, right? And then get the cubed on it. Or I could do the exponent rule because it's written with an exponent. If I do the exponent rule, I could get 2 to the 9th and x to the 4th. 4 times 3 is not 4. 4 times 3 is 12 out of that. So 2 to the 9th and 8 to the 3rd are the same number. I don't have my 2 to the 9th memorized. I'm going to do a little help here. 512. Should have known that. Pretty common number. 512 x to the 12th. If you had done 8 to the 3rd, it is exactly the same. If you've done order of operations there and did 2 to the 3rd and then put the 3 exponent on, 512 is 8 to the 3rd. You get the same number at the end. It doesn't really matter what order you do that particular thing in. All right. So let's do one with a fraction in it. 3 to the 2nd over n to the 5th. All of that in parentheses to the 4th. The top part in exponent form would be 3 to the what? 8th. On the bottom, we got n to the 20th. Okay. I was going to have a calculator to work out 3 to the 8th. I would have had to have one to work out 9 to the 4th as well. So I'm just going to use the exponent rule there to help me. And I'm going to work out 3 to the 8th power. It should be a pretty large number. 3 raised to the 8th. 6,561. 6,561 over n to the 20th. So using the exponent rule is there just to work things out. Okay. There's one exponent rule that we did not talk about. It's the 0 exponent. Anything to the 0 power equals 1. By definition, anything to the 0 power equals 1. 3,846,784 or 3,846,784,401 raised to the 0 power, still 1. No matter what you raise to the 0 power, the answer is 1. Always. Okay? If something is raised to the 0 power, the answer is 1. If something is raised to the 0 power, the answer is 1. Okay? All right. That's pretty easy. We'll get sense in doing 5 examples of that. So that's pretty boring. All right. So let's talk about polynomials and what we can do with those. So not strenuous math here with this section, but just some deals with polynomials that we'll get into as we go along. So we're going to work with polynomials pretty much the whole semester. So we'll start dealing with a little bit of stuff from them today. So polynomials are terms. They have terms in them. The terms are the pieces that are separated by addition and subtraction. Terms separated by addition and subtraction. So terms are added and subtracted. These are, another way of thinking about terms is pieces. Okay, so when we talk about the terms, we're talking about pieces that are added or subtracted. Okay. Coefficients. 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 Those are the numbers in front of variables. The leading coefficient is the number in front of the highest exponent. Term. Okay, when you talk about the variables, whichever one has the highest exponent, the leading coefficient is in front of that piece. Okay, so leading coefficient, if we talk about that, that'll come up more later on than it does today. But when the next thing with polynomials is degree, and we'll talk about that today. So the degree of a term is the sum of the exponents on the variables only. Degree of a polynomial is the highest degree of all the terms. We'll see some examples of this. All right. All right. So let's look at an example, and we want to state the degree of the polynomial. A real basic thing that we're going to do here today, and this will come up more and more as we get deeper into this stuff. So, what letter are we on here? E, F, G. Double G. All right, so here we go. Let's say we had 2x squared plus 5xy to the third minus 6x. Okay, so we want to find the degree of this polynomial. To find the degree of the polynomial, you got to find the term degree. So you need to find the degree of each term. So there are 3 terms to this problem. You've got the 2x squared, the 5xy to the third, and the negative 6x. Those are the 3 terms. We want to find the degree of each term. The degree of each term is found by taking the exponents on the variables for that term and adding them up. So on the first term, the only variable is this x. And what's the exponent on it? 2. So the degree of that term is 2. On the second term, there are 2 variables on it, x and a y. What's the exponent on this x when there's nothing listed there? A 1. What's the sum of the exponents on the variables? 4. 1 plus 3. Even though they're different variables, when you're talking about degree, you're going to add up the exponents on the variables for each term. 1 on that one. So what's the degree of the polynomial? It's 4. Pick the highest of the terms. If you can find the degree of the terms, you can find the degree of the polynomial. Okay. Example H. 4x to the third, 5x squared y plus 6x to the fifth minus 7. Term degree, I'll just abbreviate that. 1, 2, 3, 4 terms this time. What's the degree of the first term? 3. What's the degree of the second term? 3. 2 plus 1. Degree of the third term. What's the degree of the fourth term? 0. There's not a variable, so the degree is 0. What's the degree of the polynomial? It's 5. Super easy, right? Nothing. That's not real hard to do there. Degree of polynomials. Okay, so finding the degree. It's the highest one of all of the terms. So looking at the terms. All right. Next thing we want to do with polynomials is name them. And the way that we name polynomials is by the number of terms. So the number of terms, we'll make a little chart. If it has 1 term, 2 terms, 3 terms, or 4 plus terms. Okay. The name, and I'll write an example over here on the right. Okay. So we're dealing with polynomials. If it has 1 term, the name of the polynomial is monomial. A monomial, prefix is M-O-N-O, that means one. Monomial is a product of numbers and variables, or just a product of variables. Okay, just one term. An example of that might be something like 2x. Could be 2x to the fifth power, but there's no addition, no subtraction. That's how it's a monomial. There's only one piece, no other terms. Okay, what would be the prefix for 2? A binomial. Okay, bicycle has 2 tires. A binomial has 2 terms. Terms are separated by addition and subtraction. So you just got to have 2 pieces that are separated by addition or subtraction. An example of that might be x squared minus 9. That's a binomial. It has 2 terms. X squared is a term. 9 is a term. The degree of that binomial would be 2. I can look at that because it's only 2 of them to compare. So just kind of tying this together with some of the other stuff. What's the prefix for 3? Tri. So a trinomial. Example of a trinomial would be like x squared plus 7x plus 12. The example of a trinomial. It's got 3 terms separated by addition or subtraction. Okay. Anything that has 4 terms or more, we're just going to call it a polynomial. We're not going to continue the pattern here. They used to call them like quadrinomials and quintinomial and all that stuff, but that died out pretty quick because that was just too much. So anything with 4 plus terms, we're just going to call it a polynomial. Okay, monomials, binomials, and trinomials, they have the special names. Those are going to be helpful later on when we start doing some stuff. We will try to that will help us decide what to do with them or how we can do things based on what kind they are. So being able to classify is important. So let's do x cubed plus 5x squared minus 6x plus 36. So there's a good example of a 4-term polynomial. Guys, this air conditioner in here, I've been in this thing for several years, and it's either burning up or it's freezing. It ain't getting in between. We'll try to keep it comfortable. But like I said, it doesn't. It's either burning up or cold in here, so I'm just trying to. I'd rather it be cold than burning up, though. All right, so let's look at simplifying a polynomial expression and then naming that polynomial, like classifying it by what it is after we've done that. So we're going to simplify and name the polynomial. Okay, simplify and name. Letter here, I. Say we had 2x to the 4th minus 3x squared plus y plus 4x to the 4th plus 7x squared minus 6y. I mean 6. Let's make that. Let's make those x's. So we just have one variable. No sense in making it 2 variables. Not that it changes anything, but it's like 3 variables. Okay. Now, if we're going to simplify polynomials and with addition and subtraction, we look to do like terms, right? What's it take to be a like term? Same variable. And so 2x to the 4th, it's got the same variable as this guy, but are they like terms? No. What's the difference? The exponent. So to be like terms, you got to have the same variable and the same exponent on that variable. So x to the 4th goes with x to the 4th. So 2x to the 4th plus 4x to the 4th would be 6x to the 4th. The exponents don't change when you add or subtract. Exponents don't change when you add or subtract, only if you multiply. Okay? Negative 3x squared and positive 7x squared would be positive 4x squared. X and negative 6x. Negative 5x. Good job. So there's the simplified version. What would we call that? A trinomial. Not hard at all. 4 parentheses 2x squared plus 5x minus 5 parentheses 6x squared minus 3x. All right. What do we do first to simplify this one? Take order of operations.
Do the 4 times 2, 4 times 5.
Okay. What property is that called? Yeah, distributive property is what we always call that. So multiplication is going to happen before the addition and subtractions. We're going to multiply 4 times both of these pieces. What about this piece? What are we multiplying times the 6x squared and the 3x? A negative 5. Okay, so when you distribute the negative sign with it. So that's going to be 4 times 2x squared would be 8x squared. 4 times 5x would be 20x. And then the next one, so I just did that distribution. Do the same thing over here. Negative 5 times 6, negative 30x squared. Negative 5 times negative 3 turns into positive 15x. Once I've done that, I'll look for like terms. Positive 8x squared and negative 30x squared together, that would be negative 22. Good job. And then we got 20x and 15x would be plus 35x. What would we classify that polynomial as? A binomial, because it has 2 terms. After we've simplified it, it's only got 2 terms, so we call it a binomial. Kind of a brief, basic introduction to some stuff with polynomials. Any questions about polynomials? Things that we've done with them here. Not getting too deep with polynomials yet. Just getting into that. All right, last section of the night. Let's get done and get out of here. I'm gonna swap to some graph paper. You don't necessarily have to, but if you've got some and you'd like to take notes on it, that's fine. But you don't have to. You can just sketch what you're seeing here, and I meant to do blue. I think you can see it better. All right. So this section is kind of a little bit separate from the other ones. It gets us into rectangular coordinates. 2.1. We get out of that review chapter and actually get into chapter 2 with this. You'll see as we go through the semester, we bounce all back and forth all semester between the review and then go to another section. We'll go back to the review and get something and then go to another section. That sort of thing happens the entire semester. So we're going to talk about rectangular coordinates. It's the same old coordinate system that you've used for years. It is nothing new. The same Cartesian plane, you may have called it that. You may have called it just the XY plane, because that's what it is. You got a y-axis that goes vertically, an x-axis that goes horizontally. So the x-axis is horizontal, the y-axis is vertical. Okay, and you have 4 quadrants. Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. In that order. Okay, start at the top right, that's quadrant 1, and go counterclockwise. So 2, quadrant 3, quadrant 4. So when it asks you where an ordered pair is, it's saying what quadrant is it in. So when you're dealing with ordered pairs that are in quadrant 1, ordered pairs, when we talk about ordered pairs, we're talking about X, comma, Y. Ordered pairs in quadrant 1, positive X's, positive Y's. In quadrant 2, the X's are negative, but the Y's are still positive. Okay. Quadrant 3, everybody's negative. Negative X, negative Y. And then in quadrant 4, you have positive X's and negative Y's. All right, so easy stuff here. Where, let's do our first example. Example A, where is 6, negative 3? What quadrant is that in? Positive X, negative Y has to be quadrant 4. Okay? Doesn't necessarily, we don't have to go and find that point. You can, but if you just know these things, you can quickly decide, hey, it's in quadrant 4, it's positive, negative. Okay? How do would we plot that point? Go over to the right 6, 1, 2, 3, 4, 5, 6, and then down 3. 1, 2, 3, and we put it on. So X to the right is positive, to the left is negative. X comes first, and then the Y value, if it's positive, you go up, if it's negative, you go down. Simple stuff that you've done before. I sometimes mix things up, as you've probably seen. I write things backwards sometimes. So that can come into play if you're one of those folks that does that. Understand, I feel your pain. Be careful. Make sure you do X's first and Y's are second when you do your ordered pairs. If you don't, things are going to happen that can mess you up. That point right there in the center, right there, what's the name of that? Does anybody know? The origin. Yeah, y'all know. That's good. Kudos to your high school math folks. Making sure you know some vocabulary. All right. So we can plot points on a coordinate plane. That shouldn't be a big deal. Remember, X's go left and right, Y's go up and down. That should be easy to do. Let's work on graphing an equation given a table. Okay, we'll do a couple of those, and then we'll be out of here for the evening. So graphing an equation. I know some of us may remember that there are better ways to do this, but we want to do it with a table tonight, and we'll get into better ways later on. So, example B, y equals 4x minus 1. I'm going to use a table. I'm going to give you the x and y other x values to use. Let's use -2, -1, 0, 1, and 2. Okay. For any equation, no matter if we know what it does or not, you can always get some part of the picture by picking x values and plugging them in and working it out. So with this one, we've got some x values that I picked for you, and we're going to work it out and get the y values to go with us, and it's going to get us practice on plotting points and then drawing the graph for that equation. I know most of us have done y equals 4x minus 1, and you know that that's slope-intercept form. You can start at -1, count up to 1, that sort of thing. But let's work on plotting points with this stuff, and then we'll go to a much more difficult equation that doesn't happen to be as easy as this one. So start with plugging in -2. If I plug in -2 for x, what's 4 times -2? -8 minus 1, -9. So the y value is going to be -9. If I plug in -1 for x, -4 minus 1 would be -5. If I plug in a 0 for x, -1. Plug in a 1 for x, 3, 2 for x, 7. We get 5 ordered pairs that we've created there. I'm going to draw a little coordinate plane over here. I just want to make sure I got room. Excuse me. Thank you. Sorry if my sneeze was loud. They're loud. My wife complains. But to her credit, I do nothing to make them quieter. So -2, -9. What quadrant is that in? 3. So I know I'm going to be in this area down here somewhere. Okay. -2 down here, -9. I got to count 9 down to get there. Okay. -2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. -1, -5. -1, 1, 2, 3, 4, 5. 0, -1. Start at the origin. Don't move any. Go down 1. 1, 3. 1, 1, 2, 3. There it is. 2, 7. 2, 1, 2, 3, 4, 5, 6, 7. Just enough room. We get those. Makes a straight line. Most of us probably knew that was a linear equation. It was going to make a straight line, and we could connect those with a line if we want. That's beautiful. We plotted some points. We graphed an equation. I plug it in some x values. Any equation throughout this whole semester, go to Math 110. Any equation that we've got there, you can always get part of the graph by plugging in x values. Never forget that, because a lot of times you can get an answer. Like when you get to the final exam, if you don't remember how to do the problem, sometimes the graph will help you. So picking x values and working it out can help you out of that. Let's do one more. Do a little bit more fun graph here. Let's do y equals x squared minus 4. So one that's not quite the straight line here. And I'm going to pick some x values. I'm going to pick the same ones because I'm boring like that. So -2, -1, 0, 1, and 2. And let's see what this one does as far as the picture goes. So we're going to plug in those numbers. So when I square -2, what do I get? -2 times -2 is 4. 4 minus 4 is 0. So I got a 0 right there. Plug in a 1, -1. I get 1 minus 4 is -3. Plug in a 0. I get -4. Plug in a positive 1. Do I get something different than I got when I got the -1? I got the same thing back, -3. Plug in a positive 2. 2 squared is 4. 4 minus 4 is still 0. That's weird. I'm going to draw the coordinate plane here. So y-axis, x-axis. I had a student one time, they didn't know I had a straight edge up here, and they thought I was drawing that freehand as straight as an arrow. I let them think that for a while. I felt bad for them, though. They really. So -2, 0. That's right there. -1, -3. It's right there. 0, -4 is right there. 1, -3 is there. 2 zeros there. We get this. It's the shape that we're dealing with here is called a parabola, but it's kind of a U kind of shape out of that. That's what that one looks like. But we could get the general idea of what's going on there. We may not know how smooth this is just by those ordered pairs, but we get the general idea of the shape of that. Okay, so we're picking x values, plugging them in, and finding y values that go with those. Okay, so plotting points, knowing your coordinate system is going to be key to a lot of things that we do throughout the semester. All right, so I'm going to write up some suggested problems here on the screen, and with the suggested problems, these are not problems I'm going to take up, but they're problems that you could work some of. Obviously, I'm not expecting anyone to do numbers 1 through 93 the odds. My suggestion is, as you get the textbook, do a few from this. You know how a math textbook is. It'll have a section that's this kind of problem, a section that's this kind of problem. Do a few from each section. If you can do those and get them correct, then you're probably okay with that section of material. Move on to the next one. Just do 2 or 3 from each little subset into each section there. Don't do 1 through 93. There's no sense in you do 40 problems from section 1 out of that. Do the odd ones because you'll have the answers to those in the back of your textbook. So you can tell if you got it right or not. If you didn't get it right and you can't find where you did it, that's where you send me an email. Section R.2, numbers 1 through 47, a little smaller set there. Didn't do as much stuff in R.2. R.3, 1 through 43. And if you get the newest edition, the 12th edition, then same numbers. If you found a used 11th edition and you want to buy it instead of the 12th edition, I'm okay with that because I'm not going to take up the problems. The problem sets will be very, very similar in each section out of that. I've looked at both textbooks. Last section was 2-1, 1 through 59. Now here's what's happening this week as we finish up here.